So, having looked at thermal conductivity, now we can look at thermal diffusivity, which is another other property associated with thermal energy efficiency and things like that. Now, this one is thermal diffusivity or volumetric heat capacity. It is a simple additive property. For example, if I have some moisture, say some theta degree of saturation, then it will cause increase in the moisture content and mass will increase by the amount of moisture. So, supposing I am trying to find out the mass per unit volume density. Density is very simple, mass of the dry material per unit volume plus mass of the moisture simply per unit volume. So, in the total volume, what is the mass? Now, in a porous material I take the bulk volume. So, bulk density we talk of. So, it would be simply additive property, whatever moisture has gone in 1 meter cube, that will add to the density, right. It was air density of air is neglected. So, just added. Similarly, specific heat is also as a additive property, because it is the amount of heat required to raise the temperature to 1 degree, right, through unit mass, raise the temperature of unit mass through 1 degree, and that if you add another material, you will simply add that quantity. So, these are additive properties. So, rho c is the volumetric heat capacity is simply an additive property. So, rho multiplied by mass of the water plus specific heat of water, because air specific heat we neglect or density is also negligible. So, specific heat subscript W stands for water. So, thermal diffusivity is alpha divided by K by rho c, and if you see with degree of saturation, thermal diffusivity varies in this manner, right. Relative variation is small. Even for all the materials that we deal with, their specific heat varies very little. The ratio of specific heat of these materials to water, that is the specific heat in CGS unit. Ratio of specific heat, if I put it in joules per kg per degree Kelvin Kelvin. So, this ratio of any solid to water for concrete etc., it varies only from about 0.18 to about 0.24 or even less 0.2 to 0.24. So, the variation is not very large, they are very less, right, while it will be slightly. So, and if you see the values of this rho c, C particularly, you will find that it is around 1000 joules per kg. For most, some will have 1100, 1200, some will have 800, 900. So, they do not vary much, but also C does not vary much, but water has got something like 4000, somewhere around 4200, somewhere around that level. So, the ratio is around, it varies, variation is relatively small, while thermal conductivity can vary from material to material. Something for aerated concrete it can be 0.01 or 0.2, for some solid concrete it could be 2 or 2.5. So, the variation is much higher, and if it is moist, the variation we have seen that it can be 3-4 times increase, while specific heat do not vary so much. But simply one can write it in this manner, rho c, one can write the rho c in simply in this manner. So, this model, and you see degree of saturation, thermal diffusivity do not vary that significantly, not as much as rho c into multiplied by 10 to the power -7. So, does not vary very serious. Thermal diffusivity do not, it is a ratio. So, rho c do not vary much, thermal diffusivity also in that sense varies, only the conductivity. So, for this, that is what it is. So, one can simply model this very simple, there is no complicacy involved in it, one can just simply model this thermal conductivity and diffusivity you can find out in this manner. So, they are of the order of 10 to the power -7, right, meter square per second, most of them. So, that is what is for concrete, some concretes it will be something of this order, another concrete it will be of another other order. So, by and large then all putting it, summing it up all together, for this kind of material thermal conductivity mainly depends on for concrete it depends upon aggregate type, for bricks it will depend upon the solid, because fire bricks will have different, ordinary bricks will have different, fly ash bricks will have different, and so on. And then largely depends on porosity, nature of pores, and moisture content. Now, what is nature of pores? Nature of pores means how much how much proportion of it is actually closed and how much proportion of it is relatively open, relatively closed and relatively open. So, it depends upon that, because if there is a pores which is closed inside solid, it will allow for the heat to pass around it, and if the pores are larger pores with solid which surrounds the solid, it will block the path, and conduction path will be only through the connecting part of the solid itself. Therefore, the nature of proportion of this porosity is important, and this such a thing can be related to Mercalli intrusion porosimetry. Last class I was mentioning you, because through Mercalli intrusion porosimetry you can find out what is called the volume of pores versus the radius of pore. How? Essentially you have a sample which is first evacuated, small sample which is first evacuated, let us say evacuated, and then submerge it into mercury, submerge into mercury at atmospheric pressure, So, evacuated to let us say 1 micron level or such level of evacuation, then allow it to submerge it into water, I mean the mercury. Mercury will penetrate at atmospheric pressure, then apply more pressure, because mercury is a non-wetting liquid. It, as you recollect, it will form something like this on solid. So, you want to make it to spread, you have to apply pressure. They do not go into the pore on their own, where water is a wetting liquid, water is a wetting liquid. So, in case of water you get something like this, in case of mercury you will get something like this, because of the contact angle, surface tension property. So, you want to bring it to this level, you have to actually push. So, in fact, in a capillary there will be a depression, capillary depression, I mean not to this, water will be somewhere up, there forming a meniscus. If it is mercury, it will not penetrate, it will have capillary depression, in fact, in a capillary. So, you want to bring it to the same level, you have to actually exert pressure all around, So, then mercury will go up. So, as the pressure increases, and it is a function of the pore size, because it is given by surface, I can actually equate and find out. It will be related to pressure pi r square, very simple of course, let us do it quickly. Pi r square into P, the pressure I am applying, must be equals to twice pi r, twice pi r into twice, I mean I might denote it by sigma, or I do not know what did I use, S twice pi r s, and then there will be a contact angle theta, cos theta. So, this would be there, cos theta, contact angle will be involved. So, basically r will cancel out, pi cancels out, pi r will cancel out. So, it is basically P is inversely proportional to r, rest all is okay for you. So, twice pi r, rest of this thing, and it depends upon the contact angle. So, mercury has a contact angle for most of the solids more than it is 90 degree plus 90 degree plus, for glass it would be something like 140 degree. So, mercury has a contact angle much higher, therefore, this angle I am talking of, this angle, this is the angle which is more than 90, therefore, it forms a kind of a sort of a globule rather than wetting. So, if you apply higher pressure, it goes into the pores, and I can actually monitor the volume of pores. So, I can find out delta V intruded as a function of R. So, at each R how much it has gone in, I can find out, but what happens is when you actually do a test results, you will find that this is a kind of curve, this is your P versus V, right, P versus V, or I can write this would be actually proportional to 1 by R, that I can find out with respect to R, but for this class I am not really interested in that. So, P versus P, and when you actually release the pressure, the mercury comes out, but it does not follow the same path. So, this is my return path and it comes out and some mercury is retained. This is called retention, this is called retention, and fraction of retention you can find out, because this divided by this is a retention fraction. Now, retention fraction depends upon the nature of the pore. For example, there is something called ink bottle pores, which has got narrow neck, but wide inside, something like this, wide inside. So, when you release the pressure, at higher pressure some mercury comes out through this, but there will be large amount of mercury still entrapped, till it will remain entrapped. So, therefore, this is a measure of the kind of enclosed pore, pores which are surrounded by solid on all directions roughly. So, this retention fraction can be related to fraction of enclosed pores, right, something like this. So, retention fraction. So, experimentally you can get some idea related to some idea related to how much is the pores which are enclosed pores. So, this also can be determined. So, this is I think deals with the thermal conductivity part of it, most of it for porous material. So, we said that we were saying that it depends upon the volume of pores, nature of the solid, volume of pores and nature of the solid, volume of pores and nature of the solids, right. It depends upon volume of the pores and nature of the volume of the pores, right. So, as we said, depends upon nature of pores, porosity and nature of pores. So, this is the nature of pores part that I just mentioned, and moisture content. So, it will depend upon, for concrete it will depend upon aggregate type, because that forms the bulk, 70% of the volume of concrete is actually aggregate volume, and this we have done already. Equivalent conductivity we have seen that. So, this conductivity of the solid would depend upon mineralogical composition. For example, quartz conducts more compared to many other minerals, right. So, that is the highest. So, because of the crystalline structure of it. So, if you look at rocks, oven dry state, you will find basalt rock will show a conductivity of 4.40, and in the saturated state something like this. Then if you look at quartzite, that is what I was saying, which origin is quartz, 8.64, 8.58 to 8.64, not much of an increase actually, because saturation moisture content is small, they are not as porous as bricks, they are not as porous as bricks. Limestone, sandstone, so it depends upon nature, the rock type, and their degree of saturation is relatively small. So, moisture content finally, except this, let us say sandstone, it has got 4% moisture content at saturation, 2.83, etc., etc. So, for rocks, thermal conductivity varies with the rocks, and if you are using them in concrete, they will dominate the solid conductivity, but then one cannot use them unless one is trying to specifically generate, say, somewhat lightweight aggregate concrete or somewhat a concrete, because aggregate normally structural concrete will be used locally. But if you know, if you know that type of aggregate, you know how much will be the conductivity and how much insulation you really want to put to make it up. So, if you look at fine aggregates, if it is quartzite peat sand, this will be of this kind, right, thermal conductivity, and you can combine them, parent rock. Also you can have reverse sand, which may not have as much like quartzite origin, maybe of some other origin. So, one can find out thermal conductivities of various combinations of concrete using this. Solid conductivity will vary on the aggregate type, that is what this shows. So, for basalt aggregate, for example, in dry state this is 2.6, while you come to limestone it is 1.60, it can go to 1.60, and quartzite with reverse sand is something like this. Quartzite with quartzite is the maximum. So, depending upon type of your fine and coarse aggregate original mineralogical composition, you will find the moist dry conductivity varies in this manner, and saturated conductivity might vary in this manner, and porosities, concrete porosities are relatively less, while bricks will have 30%, clay bricks, this will be of the order of around maximum 20%. So, this was related to such kind of porous material which forms large class of our construction material. And if you are trying to use, let us say, a precast concrete system, right, the wall is precast, the roof is also ceiling, I mean the floor system is also precast, or roof is also precast, then everything is a precast unit and they are structurally connected, monolithic. That would save a lot of your money, but then you got to look into this sort of aspect also if you are looking into issues of energy load and things like that. So, when you have a multifunctional system which serves, like a precast box system let us say, something like hollow core slab here, wall panel, precast wall panels on all sides, then you got to look at these properties as well. You cannot ignore these properties, because they would either they will either lead to use of higher insulation material in order to satisfy the requirement of energy efficiency and things like that, or may require less insulation. So, additional insulation and finish, that would depend upon those. Okay, so, fibrous material are the other kind of construction materials. So, generally the fibers are weaved in this manner, right, and this material heat flow might take place like this. Essentially, this is a solid fiber will conduct the heat, the air will not. So, you can talk in terms of, you can actually again talk in terms of conductivity of the fiber, volume proportion of the fiber, and K2 is the proportion of the matrix if it is in a matrix. So, in a fibrous material, let us say timber, which is natural fibrous material, you have cellulose embedded in lignin matrix, and if you have an insulation, you might have something like, let us say some matrix like epoxy or something of that kind, some matrix, and then you will have some nylon fibers or something in it. So, if it is insulation material, one is to choose accordingly. So, this is the thermal conductivity of the matrix, this is the volume proportion of the matrix, this is the fiber conductivity of matrix, and x and y are the proportion of series and parallel combination. That is what one can model as, because this is this how much is this, one can think matrix is parallel to the fiber, I mean matrix is in series with the fiber, or matrix is in parallel to the fiber, the way we looked into. So, fiber, and that could be the relative proportion of fiber, that could be, if it is simply fiber and air, then one can think in terms of that should be air also. X plus y is again equals to 1, because x is the parallel proportion like we discussed earlier. So, fibrous material, one can think in terms of this, right. So, people have also tried to put in geometric proportion of the same series parallel model combination. So, for example, this is one model, this is one model, the to the power V1 geometric mean of the proportions, right. If it is both 0.5, x is equals to y is equals to 0.67, etc. So, one have tried lot of empirical relationship with this. For granular materials such as soil, series parallel combinations, so one people have used this for similar combinations of series parallel, what we have said earlier has been used, or geometric proportion as we have used in the previous model. This is the geometric mean, where K1 is the one form of conductivity, series conductivity, K22 is the parallel conductivity, or if there are two materials, even there people air, for example, air and solid, one can use geometric mean. So, fibrous materials are something of this kind. Now, wood, if you look at it, there are some empirical models. For example, K, this is in BTU fit, because the empirical model, so units are important. So, that is in FPS unit, British thermal units, feet square, Fahrenheit an hour, that is the old experimental work they did, and D stands for Owen-Wright density, right. So, some of these empirical relationships are of this form. Moisture content, for moisture content here, this is another relationship with moisture content, right. So, linear relationship, as moisture content increases, Owen-Wright density. So, this is another relationship for moist conductivity of wood. There are some more empirical relationships of this form, oven dried and at any moisture content. So, there are some empirical relationships of the kind people have tried for timber. The basic difference between granular porous material or this is that they are here we have fibers. Again the complete modeling based on fundamentals not available. This is given in book by A.W. Pratt. So, a large number of data they have generated from earlier works. A.W. Pratt heat transmission of heat in solids. So, you get some empirical models. So, that is about thermal conductivity of varieties of materials that is generally used in construction, that is generally used in construction. So, after that we will look into, so far so what we have done is we have tried to look into some materials like concrete, the issues related to concrete. So, we tried to look into the carbon dioxide issues of concrete. Then we looked into also recycled aggregate system, how do you make it more sustainable with recycled aggregate. Then we look into the operational energy side of all these kind of materials. Now, next we will look into bricks, because we see still till even today we use large amount of clay bricks. We use large amount of clay bricks even today. So, it is important to look into them, although their thermal performance point of view, thermal conductivity etc., we looked into, but let us see how these are produced, fire clay bricks. So, generally these are burned in kiln, these are generally burned in kiln, and modern fire clay bricks are formed in three processes. So, first is dry press, you can have dry press, even in extruded process can be used, and soft mud process. This is the most common that is used in Indian scenario, right. It is economical also. It starts with the raw material. What is the raw material for brick? Clay, and sometime with 25 to 30% of sand to reduce down the shrinkage when you vitrify them. These are the ingredients generally of bricks: silica, alumina. This is for surface clay bricks. As I said, this can be my ground. So, what I do is I remove a part of the organic soil is removed, organic clay is any organic material etc. So, top layer is removed and get into the surface clay. If you go further down below, you get shale, which is another form of clay, and they are they are compressed, naturally compressed over a longer period of time into that level. And if you go further down, then only in certain places you get fire clay, which has got more Al2O3 component, and that is more dense and requires much higher temperature to bring it to a fused state. So, fire clay bricks are produced at higher temperature, and therefore, it can sustain higher temperature. You produce them at 1800 degree centigrade. So, till you go to 1800 degree centigrade, nothing will happen to it. So, they are used as refractory material. So, let us look at the ordinary surface clay bricks, that is what we are looking at, which is used mostly in building. So, you will have silica present in them, alumina, lime, iron oxide and magnesia. So, this is what is present normally in the clay. Majority is 50 to 60%, right. Even in sand you will get similar sort of thing. So, first what you do, the clay is first grounded, mixed with water to desired consistency. Same concept, you want to make it plastic, otherwise you can't mold it. So, you add water to sufficient level to get the desired consistency, and then pressed into steel mold with hydraulic press, that is a better one, right. Press, and this shaped the shaped clay is then fired to about this to achieve the basic strength. So, in the process what happens, this clay all form solid solutions. They at that temperature they form kind of solid solution. First level, of course, the water smoking would be there. The water that you have added, that will smoke out, right, and then at high, one can look even at the phase diagram. I am not sure whether I have it or not, I will see that, but at higher, as you go at a higher temperature, they come to a fused state and form into almost as one single uniform mass with lot of pores, because the water would have gone, and water would have gone through the surface only. So, therefore, large amount of interconnected porosity remains. Whether you chemically filled in this, if you see the similar other material like concrete exactly is chemically combined, this is vitrified. Now, when you chemically combine also, the originally water filled space in the plastic system is filled in by adsorption product, chemical reaction product. Here the water will go away and the solid even might shrink, so leave the pores. So, therefore, that is why these materials are all porous, and if you put them in water, obviously water will be absorbed because interconnected pores will have, water would have come out through the surface only. So, left pores which are exposed to surface and interconnected system and so on. So, that is what it is. So, basically this is what you do to achieve the strength. Strength increases and water absorption reduces with firing temperature. So, if you increase the temperature, for the fusion you require higher temperature, strength will increase, and type of firing has got little effect, because type of firing that has got little effect on the properties, right. So, first step is clay mixing, then shaping or molding, use water and get it to the mold. Then you do a little bit of drying, sun drying or some sort of artificial drying. So, these are called dry green bricks, dry green bricks, and then fuel firing, so fired clay bricks. So, that is what you get. Good lot of it in Indian scenario is hand molding, right. Okay. For burning you might use biomass waste, some fly ash with low calorific value as internal fuel also you can use, because they will have some carbon in some areas, so that is the Indian scenario. Some zones people will also use a little bit of fly ash, because that is also clay and it will have some low calorific value because internal fuel will be there. Loss on ignition, higher fly ash you can use in brick, because loss on fly ash, one of the characteristics is you burn to heat it up to 1000 degrees centigrade, find out what is the loss of mass, that is we call it loss on ignition. So, more carbon means higher loss of ignition. So, you can use them in brick production actually. Clay preparation through pug mills, tractor with mixers, so just mix them, and mixers in different part of the country, that is what it will look like, that is what it will look like. So, they will dig out the clay, top clay has gone, top clay is gone, from there they are trying to collect the clay. Then during soil mix preparation, water is added to the soil. After water addition, the typical moisture content of the mix is around 25 to 30%. This is consistency. So, you got to get a consistent plastic mix, but not too much of water again. So, order would be something of this kind, which you have seen in cement also of the similar kinds, it will be slightly higher here. At this stage, fuels such as rice husk, sawdust, powdered coal can also be added, which will burn themselves out, right. These fuels added to the soil during soil preparations are referred as internal fuels. So, you can add some internal fuels. The soil, water and fuel are mixed into homogeneous mass. So, the rate of production is 2 to 4 persons per hour, person hour to produce 1000 bricks, 2 to 4 person hour to produce, if you on an average basis one can find out. Then this is molded. So, simply hand molded. As I said, 99% of the Indian scenario is hand molded. So, this is hand molded, that is what they are doing, preparing the hand mold. This is the Indian scenario, not the best thing to do, right, but then this is the scenario right now. And typical energy requirement for hand molding is estimated 15 to 25 persons hours for molding 1000 bricks, right. So, this was this time, this is for mixing, you need 2 to 4 person-hour for 1000 bricks, just for mixing 2 to. So, here the energy is per person because it is all manual, but if you convert it into mechanized system, things will be different anyway. Then this drying, freshly molded green bricks, they are, the unbaked bricks are referred as green bricks. So, they are not anything greener, but in the terminology, similar terminology we are using also for concrete, green concrete, the plastic concrete earlier we were using, not the green today we understand, right. So, referred as green bricks contain about 25% moisture roughly, then they are left in open for drying and stacked to reduce it down to 3 to 15% moisture content. In case of artificial drying, fuel burnt is to supply energy required for the drying process. You can have, for example, hot air blowing or some kind of artificial drying. So, drying of 1000 bricks in a dryer by burning fuel requires this much megajoules, 2900 to 8200 megajoules of energy. So, this is what it is. So, per 1000 bricks, because 1000 bricks, every brick has got around 25% of moisture, and you want to cut it down to 3 to 15 whatever it is. So, this is the kind of energy required. Removal of mechanical moisture or drying of bricks below 200 degrees centigrade, first step of firing. So, obviously, the free moisture will go away, here. So, moisture will be removed below 200 degrees, and then of course, if there are carbonaceous matters inside, like you have added fuel, internal fuel, they will burn, and endothermic decomposition of the clay will decompose, absorb heat and decompose, right, and evaporation of chemically combined water, that is what I was saying. So, same thing, something similar happens, because some of them will have water of crystallization type, chemically combined water, silica aluminum system, and that would go out when you heat to about 600 degree, up to about 600 degree. So, similar up to 200 degree centigrade, free water goes away, which are not chemically combined. 400 to 600 degree centigrade, any chemically combined water will go away, and decomposition of clay takes place, something of this kind, Al2, this is the structure, let us say Al2O3 2S2O. So, it is actually in our cement C2A, it is a kind of structure of C2A, not C2, sorry, S2, sorry, S2A, no C2, so much. So, this will go out now, this will decompose into oxides, this will break into oxides. So, this is what happens, and enthalpy change is 1.6 kilojoules per kg of kaolinite. So, if you take kaolinite clay, this is the kind of energy you require per kg of kaolinite, right. Calcium carbonate, which is an impurity in soil, that will also break down into carbon dioxide and calcium, but usually this is not much, right. So, 600 to 800 degrees centigrade, it will be complete, and its delta, its delta H is this much, 7302 kilojoules per kg of calcium carbonate. Then there is a vitrification. During vitrification, so first stage is what? Water smoking, water goes out. Then clay minerals, they decompose, taking heat, right, break down into aluminum oxide, silicon oxides, and any combined water, that will go away. And then, or calcium carbonate if it is there, it will, magnesium carbonate if they are there, they will actually decompose. So, oxides are now left. This, during vitrification process, new mineral phases are formed, including liquid phases, which on cooling set as glass phases and provide strength to the fire break. Vitrification is generally an exothermic process. So, it gives out heat. So, after that you start, as the temperature increases, then they all get combined into new kind of solid solution form, and some different phases are formed on cooling, and that gives you the strength. So, this is the phase diagram, this is the phase diagram, right, this is the phase diagram depending upon the percentage of aluminum. So, if you have high percentage of aluminum, you can see that heating required is temperature at which actually you will get the liquid to solid phase, I mean it remains liquid. So, this is at higher temperature, percentage of aluminum higher, generally this will be lesser as we have seen in our case, and the phases formed are mullite as a crystal plus alumina, this is mullite. At higher temperature, this is what higher percentage of alumina, this is what you get, whereas at lower percentage of alumina, liquid is here, then it solidifies into this kind of stage. So, this is the kind of phase diagram for SiO2 Al2O3 system. Okay. So, natural clay, we have fluxes like sodium oxide, potassium oxide, calcium oxide. Okay, just one point, if it is all alumina, obviously melting is, it will remain solid liquid till this, then liquid plus alumina. So, it remains liquid for higher temperature, but if you add silica together with it, so as you come along this direction, the temperature, this liquid level temperature up to which it is liquid actually reduces down, and at this portion it is if you heat up to this 1600 degree centigrade, you will get a liquid stage if you heat it up and then cool, of course, cool, then this is solid level. So, anyway, this is not really that important for us, but these fluxes are usually there, sodium, potassium, calcium, magnesium, and they lower the melting point, melting temperature. Okay, one can represent this equilibrium diagram in triangular phase. Ternary system of sodium, silicon, alumina can form much lower temperature, so at 1050. So, if you have a ternary system of sodium oxide, I mean silicon oxide, silica and alumina, they can form the they can actually, you can heat it up to much lower temperature to melt them. So, this is the kind of equilibrium diagram. This is Al2O3, this SiO2, this sodium, and such combinations are available, and I do not think I will go into that discussion, but generally temperature would be 1050 2000 around 1050 plus 1200 degrees centigrade, you heat them up to. So, as you are increasing firing temperature and time, generally increasing firing time from 120 to 480 minutes have no strength in change. So, temperature here, compressive strength, but temperature has got a role. Higher the temperature, you find the strength increases. So, your energy required would be higher as you go higher, but time does not have much of a meaning. Once everything is molten, you cool it and you get the strength. So, these are the values 4.47 to 24.47 is a brick strength MPa, all right, and water absorption will obviously reduce. Higher strength, water absorption reduces, right. So, this is what we will discuss in the next class, types of kiln where we produce in India, reports are actually available, but this is actually this as you shall see, this is highly energy intensive and also obviously labor intensive. So, that way you are not really using the other kind of like energy from other sources, but highly, even clay bricks are quite energy intensive. Also you are using surface clay which might be used for agricultural or other purpose, and since you are using a lot of fuel, you might be generating a lot of carbon dioxide, although the production process may not generate carbon dioxide. As long as you use waste material, it is all right, but if you are not using waste material, then the carbon dioxide issue will come in. So, we will look into the types of trends in the next class.